Okay, I want to continue our discussion of antiderivatives and see if we can start getting some antiderivative formulas for some familiar functions. So let's suppose I wanted to find this. Remember, I can call this the indefinite integral of x squared. I can also call it the general antiderivative of x squared. And I pretty much know if I can find an antiderivative, I'm just going to add a constant to it. Adding a constant doesn't change the derivative. Geometrically, what it does is it just vertically shifts whatever function I found here. Okay, so I need to find a function whose derivative is x squared, and I'm going to use just what I call the guess and check method. Okay, so I'm going to come up with a guess. Now, take a moment, come up with your own guess. If you need to pause the video, come up with your own guess. Okay. Now, what you might have come up with is x cubed. Okay. Because I'm thinking with the power rule, I know that when I take the derivative, I'm going to get the power goes down by 1. Now, it turns out that this guess is wrong, okay, but it's close, and it's going to be easy to fix. So if you actually came up with the exact right guess, fantastic. But if you just come up with something that's close, very often that's going to be good enough. Because what I'm going to do is I'm going to check this. I'm going to take the derivative, and I'm going to say, oops, the derivative of x cubed. And I say, that gives me 3x squared. Now, I wanted the x squared. I didn't really want the 3. So I'm going to adjust. So I'm going to try instead 1/3 x cubed. Because that way, I'm going to have this 1/3 by the constant multiple rule. It'll be hanging out. It's going to cancel with that 3. So let's check that. If I take the derivative of 1/3 x cubed, when I bring that 3 down, it cancels with the 1/3. So I get 3 times 1/3 x squared, which is just x squared. So I'm going to say my antiderivative is x cubed over 3 plus c. That gives me the general antiderivative, or the family of all functions whose derivative is equal to x squared. Okay. Now again, I'm using this notation for the indefinite integral. The book isn't using that yet, so the book would just say, find the general antiderivative of x squared. They'd use words rather than symbols to ask the same question. Okay. Now, you might have, some of you guessed this initially, which is fabulous. But I purposely wanted to show you what happens if we get the wrong guess, because it's then easy to fix. And sometimes it's actually easier to say, I'm going to guess this even though I'm pretty sure it's going to be off by a constant, because it's going to be faster for me to see what constant it's off by and then fix it than it is for me to puzzle out ahead of time what constant I need. Okay. All right, so let's try another one. Let's try the general antiderivative of x cubed. So same thing, I'm going to have to get a particular antiderivative, but then I can just add an arbitrary constant to it, and we're good to go. Sometimes this constant gets written as a capital C. That's what your textbook tends to do. A lot of times you'll see it written as a lowercase c, and it does not matter. Okay. All right, so I'm going to again try the guess and check method. So I'm going to guess. And I'm going to guess x to the 4th. Now again, I'm pretty sure that that's wrong. I'm pretty sure I'm going to be off by a constant, but I'll be able to adjust. So I'll check. If I take the derivative of x to the 4th, I'm going to get 4x cubed. I wanted the x cubed, I don't want the 4. So I'll adjust. I'll try 1/4 x to the 4th. And if I check that, I get the derivative of 1/4 x to the 4th is just x cubed, which is what I wanted. So I can write this as x to the 4th over 4, or as 1/4 x to the 4th. They're equivalent. Okay, now both of these were power functions, and I'm sort of noticing a pattern. It looks like when I integrate, or when I find an antiderivative, the power goes up 1. And that makes sense because I know that when I take the derivative, the power goes down 1. So let's see if we can do this more generally. Let's see if we can find an antiderivative of x to the nth, where all I'm saying is that that's a fixed power, but I'm not specifying which power it is. And again, I know I'm going to get a particular antiderivative plus an arbitrary constant. So if I'm going to guess, I would guess x to the n plus 1 would be the function whose derivative I would get. Now I think I'm probably off by a constant, but I know that when I take the derivative, the power is going to go down 1. So I check, and I say the derivative of x to the n plus 1 would be n plus 1 times x to the n. So I do have the x to the n that I want. I'm off by this constant, n plus 1, so let's adjust by dividing out by that constant. So let's try 1 over n plus 1, that's just a constant, times x to the n plus first power. So now I check, I'm going to take the derivative of 1 over n plus 1 times x to the n plus 1. Constant multiple rule, I get that same constant times n plus 1 times x to the n. The constants cancel, and I just get x to the n, which is what I wanted. I like it. So it looks like we get x to the n plus 1 over n plus 1. So essentially the rule for integrating a power or taking an antiderivative of a power function is you raise the power by 1, divide by the new power. Okay? All right. There is one power, one value of n for which this doesn't work. Take a moment and see if you can see what value of n that won't work for. I'll give you a hint. We can't have a 0 in the denominator. So if n was -1, that would make a 0 in the denominator. So this is true as long as n is not -1. Okay. So for any other power, I can use this rule that we're going to raise the power by 1 and then divide by the new power. Let me just show you a couple more examples where that works, and then we'll return and take a look at what if the power is -1. So let's say I wanted to find an antiderivative of the square root of x. Well, this is very similar to if I wanted to take the derivative of this. I would first rewrite that as a fractional power. So I would say I'm taking an antiderivative of x to the 1/2 power. So I know I'm going to get an antiderivative plus c, plus an arbitrary constant. So 1/2 plus 1, see, that would be 1/2 plus 2/2. It's going to give me 3/2. So I'm going to get x to the 3/2, and then I'm supposed to divide by the new power. Well, dividing by 3/2 is the same as multiplying by 2/3. So an antiderivative would be 2/3 x to the 3/2. All antiderivatives would be this function plus an arbitrary constant. Let's suppose I wanted to integrate 1 over x squared dx. Again, similar to what I would do if I were taking the derivative of this function, first thing I want to do is rewrite it as a power. So I would rewrite that as x to the -2. Now, be very careful here. The new power is 1 more than this. A lot of times people want to say that's -3, but -3 is what I would get if I subtracted 1 from this. -2 plus 1 is actually -1. So when I have a negative exponent here and I add 1 to it, it almost looks like it's getting smaller because the absolute value is getting smaller, but I'm still adding 1 to it. So this would be x to the -1 divided by -1 plus c. And I'd probably just rewrite that as -x to the -1 plus c, or perhaps -1 over x plus c. Okay. Any of those would be perfectly acceptable. Okay. So, just like when we were taking derivatives, roots and reciprocals of powers, we can get using this power rule. Okay, so now let's take a look at what if x is, or what if n rather, is negative 1. So I want to integrate x to the negative 1 dx. And I know I cannot use the power rule because if I add 1 to this, I'm going to get 0, and I can't divide by 0. So this is the one power where it's actually not helpful to have it written as a power. It's actually easier to see what's going on if I write it like 1 over x. Because then I can say, let me rack my brains. Let me see if I can think of a function whose derivative is 1 over x, and then I'll just add c to that. Now, a lot of times people say, oh, natural log of x, because the derivative of natural log of x is 1 over x. You are correct that that is the derivative, but natural log of x isn't the general antiderivative of this. And let me show you why. Oops. I want to draw two graphs here. Okay. So, if I have, I'm going to just write, well, let's write f of x for our antiderivative, and little f of x, which will be big F prime of x, which will be 1 over x. So I'm thinking of this as the derivative of something. But if I look at 1 over x, it's defined everywhere except at 0. Okay. So it's defined whether x is positive or negative. If I look at the natural log of x, that's only defined when x is positive. So the natural log function is an antiderivative for this portion of 1 over x. But if I'm trying to find an antiderivative for the function, I don't want to find an antiderivative for just part of it. I want to find an antiderivative for the whole thing. So I want to find something that works when x is negative as well. Now, if you remember, when we did logarithmic differentiation, we learned that if we take the derivative of the natural log of the absolute value of x, this is a very unusual function because I get the same formula I would get if there was no absolute value there. Okay. Almost every other function we have, if you introduce an absolute value, it changes the formula for the derivative. What introducing the absolute value does here is it just extends the domain, but we get the same formula for our negative values. Okay. So, this is what the natural log of the absolute value of x looks like. This piece over here is the antiderivative for, is an antiderivative for this piece of graph. This piece over here is an antiderivative for this piece of graph. And so my general antiderivative for 1 over x is going to be the natural log of the absolute value of x plus c. I can't, when I integrate, get that the domain for my antiderivative is smaller than the domain for the derivative function. I need it to be an antiderivative for the whole thing. Okay. So that's what we do if our power is negative 1. Antiderivative of 1 over x is natural log of the absolute value of x plus c.